In this video, uh, the following topics will be covered: K-Medoids and hierarchical methods. The K-Medoid clustering method, it's a partitioning around medoids. It starts from an initial set of medoids and iteratively replaces one of the medoids by one of the non-medoids if it improves the total distance of the resulting clustering. Partitioning around Medoids works effectively for small data sets but does not scale well for large data sets. Efficiency improvement on the partitioning around Medoids, Clara and Clarence. The partitioning around Medoids algorithm is a popular realization of K-Medoids clustering. It tackles a problem in an iterative and the greedy way. Like the K-means algorithm, the initial representative objects, called seeds, are chosen arbitrarily. We consider whether replacing a representative object by a non-representative object would improve the clustering quality. All possible replacements are carried out. The iterative process of replacing representative objects by other objects continues until the quality of the resulting clustering cannot be improved by any replacement. The quality is measured by a cost function of the average dissimilarity between an object and representative objects of its cluster. Like the K-means algorithm, the initial representative objects are chosen arbitrarily. Each time a reassignment occurs, a difference in absolute error E is contributed to the cost function. Therefore, the cost function calculates the difference in absolute error value if a current representative object is replaced by a non-representative object. The total cost of swapping is the sum of costs incurred by all non-representative objects. The K-medoids method is more robust than K-means in the presence of noise on an outlier because a medoid is less influenced by outliers or other extreme values than a mean. Specifically, let O1 to OK be the current set of representative objects, that is known as medoids, to determine whether a non-representative object denoted by O random is a good replacement for current medoid OJ. Calculate the distance from every object P to the closest object in the set F. So use the distance to update the cost function. The reassignments of object to new medoid are very simple. The diagram shown on the screen is explaining the partitioning around medoids. It's a typical K-medoids algorithm. The first square on the screen is showing the data points and k value equals to 2 is assumed. Then arbitrarily choose a k object as initial medoids, that is shown in the second square as in the dark blue color. Assign each remaining object to the nearest medoids, so the cluster has been formed. In the fourth one, randomly select a non-medoid object or random. Then the fifth square, it is showing the compute the total cost of swapping. The last one swapping O and O random if the quality is improved. This is the algorithm of K-medoids. Partitioning around medoids, a K-medoids algorithm for partitioning based on medoid or central objects. K is the number of clusters and D is the dataset containing the n number of objects. Output from this algorithm is a set of K cluster will be formed. The methods are: step number 1, arbitrarily choose K objects in D as the initial representative of objects and repeat the following steps. The first one, assign each remaining object to the cluster with the nearest representative object. Randomly select a non-representative object, O random. Compute the total cost S of swapping representative object with OJ with O random. If S is less than 0, then swap OJ with O random to form the new set of K representative objects. Until no change occurs, then repeat the steps. So in this clustering algorithm, we have two different algorithms. The first one is k-means, the another one is k-medoids algorithm. Which method is more robust, k-means or k-medoids? The k-medoids method is more robust than k-means in the presence of noise and outlier because a medoid is less influenced by outliers or other extreme values than a mean. However, the complexity of each iteration in the K-Medoids algorithm, O of k n minus k square, for a large value of n and k, such computation becomes very costly and much more costly than the k-means method. Both methods require the user to specify the k value, the number of clusters. Then how can we scale up the k-Medoids method? Uh, a typical k-Medoids partitioning algorithm, like partitioning around Medoid, works effectively for small data sets, but does not scale well for large data sets. To deal with a large data set, a sampling-based method called Clara, clustering large applications, can be used. Instead of taking the whole data set into consideration, Clara uses a random sample of the data set. The partitioning around Medoids algorithm is then applied to compute the best Medoids from the sample. Putting data objects in the form of a hierarchy is useful for data summarization and visualization, handwriting recognition, hierarchy of species, employees, gaming, and so on. Agglomerative versus divisive hierarchical clustering. A hierarchical clustering method can be either agglomerative or divisive, depending on whether the hierarchical decomposition is formed in a bottom-up or top-down fashion. Let's have a closer look at these strategies. An agglomerative hierarchical clustering method uses a bottom-up strategy. It typically starts by letting each object form its own cluster and iteratively merges clusters into a larger and larger clusters. A divisive hierarchical clustering method employs a top-down strategy. It starts by placing all the objects in one cluster, which is the hierarchy's root. It then divides the root cluster into several smaller subclusters and recursively partitions those clusters into smaller ones. The partitioning process continues until each cluster at the lowest level is coherent enough, either containing only one object or the objects within a cluster are sufficiently similar to each other. Some of the problems encountered: merging or splitting decisions, if not well chosen, it may lead to low quality of the clustering. So moreover, the methods do not scale well because each decision of merging or splitting needs to be examined and evaluate many objects or clusters. The solution for this problem, it can be combined with multi-phase clustering. The diagram shown on the screen, agglomerative versus divisive hierarchical clustering. The diagram shows the application of Agnes, that is agglomerative nesting, an agglomerative hierarchical clustering method, and Diana, the divisive analysis, a divisive hierarchical clustering method on a data set of 5 objects A, B, C, D, E. Initially, Agnes, the agglomerative method, places each object into a cluster of its own. The clusters are then merged step by step according to some criterion. For example, the clusters C1 and C2 may be merged if an object in C1 and an object in C2 form the minimum Euclidean distance between any two clusters from different cluster. This is a single linkage approach in that each cluster is represented by all the objects in the cluster, and the similarity between two clusters is measured by the similarity of the closest pair of data points belonging to different clusters. The cluster merging process repeats until all the objects are eventually merged to form one cluster. At Diana, the divisive method proceeds in the contrasting way. All the objects are used to form one initial cluster. The cluster is split according to some principle, such as the maximum Euclidean distance between the closest neighboring objects in the cluster. The cluster splitting process repeats until eventually each new cluster contains only one object.